So, how in the world did we get from believing the Earth sat on a giant turtle to, understanding a universe that exploded from a single point? That's the journey we're going on today, inspired by Stephen Hawking's incredible book, A Brief History of Time. We're going to trace humanity's ever changing map of the cosmos. Hawking kicks things off with this brilliant little story. Picture this: a famous scientist is giving a big lecture, explaining how the Earth orbits the sun and our sun orbits the center of our galaxy. After he's done, this little old lady in the back stands up. She says, "Everything you just said, total nonsense. The world is actually a flat plate and it's resting on the back of a giant turtle's." The scientist, he's kind of amused, so he plays along. He asks, "Well, what's the turtle standing on?" And she just fires back, "You're a clever one, aren't you? But it's turtles all the way down." And that story, as funny as it is, gets right to the heart of what we're talking about. For thousands of years, we've been trying to sketch out a map of our universe. But what's holding that map up? What are the fundamental truths it stands on? Our very first attempts were pretty simple. They were based on what we could see with our own two eyes. And get this, way back in 340 BC, the philosopher Aristotle was already using actual evidence to argue that the Earth was a sphere. He wasn't just guessing. He pointed to things you could go out and see for yourself, like how the Earth's shadow on the moon during an eclipse is always round, or how when a ship comes in from the sea, you see the sails long before you see the hull. This was a huge deal. It was the first big step in redrawing our cosmic map, not based on myths, but on real hard observation. So, building on Aristotle's idea of a round Earth, we get the Ptolemaic model. And honestly, it was this beautiful, intricate, and really orderly picture of the cosmos. It put us, a stationary Earth, right at the center of everything. The sun, the moon, all the planets, they all orbited us in these perfect heavenly spheres. And you can see why it stuck around, right? It made sense, it felt elegant, it matched what you saw in the sky every day. For over 1,500 years, this was the accepted map of reality. But here's the thing about science and making maps in science. Any theory, no matter how good it seems, is always provisional. It's just a placeholder until a better one comes along. So when new observations start popping up that just don't fit the map, well, the map has to change. And after 15 long centuries, a massive redrawing was just over the horizon. I mean, think about it. For over 1,500 years, the Earth-centered universe was just a fact. It's what everyone knew. And then, in 1514, this Polish priest, a guy named Nicholas Copernicus, comes along and proposes this totally radical new idea, an idea that would quite literally end up moving the Earth. The whole Copernican shift was really about one thing: simplicity. See, in Ptolemy's model, you had to have planets doing these complicated loops and circles to explain what we saw. But by putting the sun at the center, all of a sudden, those weird paths disappeared. The whole system became so much cleaner, so much more elegant. It was a better map, for sure, but it would take almost another 100 years and a brand new piece of technology for people to really take it seriously. And that new technology showed up in 1609. This is where the old map really got its death blow. It came from Galileo and his brand new invention, the telescope. When he pointed that thing at Jupiter, he saw moons. Moons orbiting Jupiter, not Earth. That single observation proved, without a doubt, that not everything in the universe revolved around us. The old map wasn't just wrong, it was officially broken. Okay, so the Earth is no longer the center of everything. The universe suddenly feels way bigger, way more open. But now the question is, how does it all work? What are the rules? Well, the laws of motion and gravity, figured out by Isaac Newton, would give us the rule book for this new cosmos, and at the same time, create a brand new, really deep puzzle. So here was the big contradiction in Newton's map of the universe. His own theory of gravity, which worked perfectly for everything else, predicted that every single star should be pulling on every other star. So why hadn't the whole universe just collapsed in on itself into one giant fiery clump? I mean, a static, unchanging universe should have basically destroyed itself by now, right? It took centuries to find the answer. And when we did, it didn't just redraw the map again, it completely blew it wide open. The universe isn't static. It's not just sitting there. It's expanding. The actual fabric of space between all the galaxies is stretching, carrying them farther and farther apart from each other. And this is exactly what astronomers like Edwin Hubble started to see. They looked out and saw galaxies flying away from us in every direction. Now, if you just run that movie backward in your head, it means that everything in the entire universe must have started out from a single, unbelievably hot and dense point. And that explosive beginning? Well, that's what we now call the Big Bang. So this new map, this expanding universe born from a Big Bang, was a massive triumph. But it also uncovered even deeper puzzles, both on the ginormous scale and the teeny tiny one. And by the 20th century, physics had developed two of the most successful theories in all of human history to try and solve them. The only problem? They gave us two totally different, completely incompatible maps of the exact same universe. So on one side, you've got Einstein's general relativity. It's this beautiful, deterministic theory for the really big stuff: planets, stars, galaxies, the whole shebang. And on the other side, you have quantum mechanics. It's an unbelievably accurate theory for the very, very small stuff: atoms, electrons, particles. But here's the catch. One is predictable and orderly, and the other is based entirely on probability and chance. Right at the heart of quantum mechanics is something called the uncertainty principle. And what it says is that there's a fundamental limit to what we can ever know about the universe. The more precisely you try to measure a particle's position, the less precisely you can know its velocity, and the other way around. And this isn't because our tools aren't good enough. It's a blurry, fuzzy property that's just baked into the fabric of reality itself. Wild, right? This randomness just drove Einstein bonkers. His famous line, "God does not play dice," just perfectly captures the huge philosophical gap between these two great pillars of physics. He just couldn't accept that the universe could be governed by random chance. But every experiment we've ever run says that, well, it is. So that brings us to the biggest challenge in physics today. Kind of the holy grail, really. The goal is to unite these two completely conflicting maps, to find one single unified theory that can describe both the very large and the very small, all at once. This ultimate map is what people often call a theory of everything. I mean, the dream here is to find one master equation, a single set of rules that can describe every single fundamental force and particle in nature, from the instant of the Big Bang to how a star lives and dies, all the way down to the quarks buzzing around inside a proton. And one of the most promising and, let's be honest, most mind-bending ideas out there is string theory. It says that if you could zoom in on a particle, like an electron, way, way, way down, you wouldn't find a little dot. You'd find a tiny, vibrating loop of energy, a string. And just like a violin string can play different notes depending on how it vibrates, these tiny cosmic strings create all the different particles and forces we see in the universe, just by vibrating in different ways. So this whole incredible journey, from turtles to an expanding universe to tiny vibrating strings, it all leads us to one last, really important question. Why? Why do we even do this? What is it that drives this relentless, obsessive quest to understand everything? And this is where Hawking gives us the simplest and maybe the most beautiful answer of all. We don't do it for some practical reason, even though amazing technologies often come out of it. We do it because we just yearn to know. We want to know where we came from and why we're here. It's just a fundamental core part of what it means to be human. So from a flat plate on a turtle's back, all the way to a cosmos born in a Big Bang, a universe that might be made of tiny, vibrating strings, our map just keeps unfolding. Our goal is nothing less than a complete and total description of the universe we live in. And really, the most exciting part is asking ourselves, what incredible new piece of that map are we going to uncover next?